myself is Divya Bahal, Assistant Professor in Chemical Engineering Department at LJ Institute of Engineering and Technology. The subject that we are going to continue is Mass Transfer Operations 2. So in this lecture we will continue with the numericals based on McCabe-Thiele method. Okay. So we studied about enriching section, stripping section and the feed line equation. So how numericals can be asked based on this topic, right? So moving forward, the first question is, a binary distillation column is operating under the conditions given below, right? You have been given feed flow rate, that is 350 kilomole per hour. Overhead product means distillate is given, that is 150 kilomole per hour. Mole fraction of more volatile component in the overhead product, that is your distillate composition is given 0.97. Your bottom product is 0.02. This is composition of more volatile component in residue. Now bottom product rate, that is residue flow rate, this is 200 kilomole per hour. Here reflux ratio is given, that is 3.5. Now read this carefully. In the stripping section, it was found that the mole fraction of more volatile component in the vapor leaving a plate is 0.33, while its mole fraction in the liquid coming to the same plate is 0.25. Assuming constant molar overflow, determine whether the feed is vapor, liquid or partially vaporized. Okay, so the data which is given 0.33 and 0.25, that is for stripping section. Okay, hence here you have to use the equation, operating line of what? Stripping section. Now what we have to find? We have to find whether the feed is vapor, liquid or partially vaporized. It means you have to find the Q value. So let's start. So basis is what? 350 kilomole per hour of feed is there. Hence D is also given, W is also given, and you have the mole fraction also. Now in stripping section the formula is what? Ym plus 1 is equal to Lm upon Vm plus 1 Xm minus Wxw upon Vm plus 1. Okay, so here it is given that the mole fraction of more volatile component in the vapor leaving a plate is 0.33. Okay, so suppose I am taking this below plate. From this your vapor leaving composition is what? Ym plus 1. Okay, and it is given that the mole fraction of liquid coming to the same plate. Okay, see, Xm is what? The composition of liquid which is coming to this below plate. Okay, so Ym plus 1 is what? Vapor leaving that M plus 1 plate, and Xm is what? Vapor liquid coming to that M plus 1 plate. Hence you are given this, instead of Lm what I can substitute? Vm plus 1 plus W. Thus what you get, the final stripping line equation is what? Ym plus 1 is equal to Lm upon Lm minus Wxm minus Wxw upon Lm minus W. So this is the operating line of stripping section. Now just substitute the value. Ym plus 1 is what? 0.33 and Xm is what? 0.25. So substituting the value, okay, and evaluating what you get your liquid flow rate in stripping section. L bar is what? Liquid flow rate in stripping section. Now Vm plus 1 equal to V bar, okay, because it is given that constant molar overflow is there. See, read the question properly. What was given? That your molar overflow is constant. Hence from assumption of McCabe-Thiele method, what we saw, that vapor flow rate in any section would be same. Therefore I am taking that Vm plus 1 is equal to V bar. Okay, for all the plates in stripping section your vapor flow is constant. Now for stripping section, what is there? That your overall balance, okay, around the reboiler. L bar is equal to V bar plus W. Okay, from that you get your V bar. What is it? It is 625 kilomole per hour. But your feed flow rate is how much? 350 kilomole per hour. So your reflux ratio you are given now. What is reflux ratio? L by D. Okay, therefore L equal to what? RD. Clear? So L is equal to 3.5 into 150. Distillate value is already given to you. See, the distillate value is given. Hence your liquid flow rate in rectifying section is how much? 525 kilomole per hour. Hence from here I can suggest that your F is how much? 350 kilomole per hour. L and V, those are for rectifying section. L is how much in rectifying section? It is 525 kilomole per hour. For stripping section, your L bar is how much? 825 kilomole per hour. So L is how much? 525 and L bar is what? 825. So the remaining, okay, 350 is what? It is from feed. Now learn the equation of Q line, how we derive. Okay, when your feed is introduced, L bar is what? L plus QF in stripping section. From it you get your Q value as 0.8572. Now see, the way Q value for different kind of feed, what is it? Okay, when your Q value is between 0 to 1, that is your partially vaporized feed. Here your Q value is what? 0.85. It means your feed is partially vaporized. This is one kind of sum that can be asked based on your stripping section and Q line, right? The next question is 1000 kilomole per hour of an ethanol propanol mixture containing 65 mole percent ethanol is to be separated. So ethanol is a more volatile component. The desired terminal composition in terms of mole fractions are 0.92 and 0.07. So see, here your feed composition is given 0.65, okay, and in a terminal composition means what? At the end, distillate composition and residue composition. So it is 0.92 and 0.07. The feed is saturated vapor and total condenser is used. When reflux flow rate is 4 times the amount of top product, find the number of theoretical stages. Here relative volatility is given as 2.1. So what are the important data here? That your feed is saturated vapor. Okay, then reflux flow rate is given. Okay, your reflux flow means liquid which is sent back to the column, that is given is equal to 4 times the amount of top product, means distillate. So and relative volatility is given as 2.1. So let's proceed. So see, we are taking basis as 1000 kilomole per hour. Okay, here it is given that 1000 kilomole per hour is your feed and XF is given. See, here alpha is given, okay, relative volatility is given as 2.1. So I can use this equation y is equal to alpha x upon 1 plus alpha minus 1x. This is my equilibrium relationship, okay. So substituting the value of alpha, I get this following equation. Now you have to generate equilibrium data, okay. So substitute value of x, point from 0 to 1, okay. So what I am doing? From 0 to 1 I am substituting the value and correspondingly I am getting value of y. So I have generated a equilibrium data, right? Now here see xf, xd and xw values are given. Right now what is given? That your reflux flow rate is 4 times your distillate amount. Hence your reflux ratio is what? R is equal to 4 is obtained. Clear? Now here you can see that you have plotted in your graph an equilibrium diagram, right? That is your equilibrium curve you have plotted. Now Q point, what is it? That is the intersection of your rectifying section operating line and diagonal, right? So from your Q point is where? It is from 0.92, that is the distillate composition, okay? So first of all plot your point Q, that is at 0.2. Now the intercept of this line is what? Enriching section. The operating line is what? This is the operating line of rectifying section. Yn plus 1 is equal to r upon r plus 1 xn plus 1 upon r plus 1 into xd. So intercept is what here? Xd upon r plus 1. So you got your r value. Now hence your intercept value is what? 0.184. Okay. So now you got the intercept value is 0.184. Draw the line on this equilibrium diagram. Feed is saturated vapor means Q equal to 0. Here you can see from the feed condition where your red block is given. Q equal to 0. It means saturated vapor is there. Okay. It means it would be a horizontal line. Your feed line is what? Horizontal. Therefore, the feed line is parallel to x-axis. You can see it is horizontal line. It is parallel to the x-axis. And the point of intersection of it with the diagonal is your 0.6565. Point N here. Okay. And in this diagram, N point. What is this? That is the intersection of feed line and your diagonal. You have been given the feed condition is how much? See here, feed condition is given 0.65. XF is what? Feed condition. So locate the point now, 0.6565 on the diagonal. So here you can see that XF equal to 0.6 is what? That is your feed point, and Q point is what? That is your intersection point of rectifying section and diagonal. Now the operating line of stripping section passes through the point of intersection of feed line and operating line of rectifying section. Draw this line through the point 0.07 and 0.07. Okay, again XW is how much here? T point, that is your residue composition, 0.07. Okay, from there draw your stripping section, operating line of stripping section, and from Q draw the operating line of your enriching section. Okay, now Remember, recall the McCabe-Thiele method. Okay, what you are doing from point Q, draw a horizontal on the equilibrium, then drop the vertical till it touches the operating line of end rectifying section. So start from point Q, okay, construct triangles which represent ideal plates between the equilibrium curve and the operating line till we cover or cross the point P, that is 0.07 on the diagonal. Okay, try to understand it. So from where you are starting to construct your triangle, from point Q till when you have to continue till you reach the residue composition, that is point P, XW. Okay, so that way you are plotting, you are constructing your triangles. Hence, what are the number of triangles plates which you get? That are triangles 9. Your last stage is your reboiler. If you are neglecting it, then the number of theoretical plates in your column is 8. Now location of feed plate. See, at stage 4, see the feed line which is horizontal, that intersects with rectification section line and the stripping section line. When the three lines intersect with each other, that stage is your feed plate. Hence your feed tray is 4th plate. So this way you plot number of stages on the graph using McCabe-Thiele method. Now the third question which can be asked in exam is, a continuous rectification column is used to separate a binary mixture of A and B. Distillate flow rate is given as 100 kilomole per hour and its composition is 98 mole %. In enriching section, the mole fraction of A in liquid and vapor from two adjacent plates are given. See, two adjacent means I am talking about 1 and 2 here. Okay, 1, 2 adjacent. If latent heat of vaporization is same for all mixture. Okay, see, this is the assumption of McCabe-Thiele method, that molar latent heat of vaporization is constant. Okay, and the feed is saturated liquid, then calculate reflux ratio and vapor flow rate in stripping section. Here A is your more volatile component and B is your less volatile, right? Feed is introduced into the column. The top product is your distillate while bottom is your residue. See, the feed plate divides your column into rectifying section and stripping section. So you can see, as you go on the top, your vapor composition increases, right? And as you go down, okay, your liquid composition of more volatile component, it will decrease. So let's see, here D is given as 100 kilomole per hour and XD is given. Now feed is your saturated liquid. It means Q equal to 1. Okay. What is the significance? Here that L bar is more than L and your V is equal to V bar. It means liquid flow rate in stripping section is more than that in enriching, whereas vapor flow rate in enriching and stripping would be same. So see how you can use the data. Okay, you are given that your feed is saturated liquid. From that you can reduce that V is equal to V bar. Now let's talk about the adjacent plate. So you can see 1 and 2 are my adjacent plate. Okay, so see here, be very careful how you are arranging your Y and X terms. So okay, you can see that from one plate the vapor leaving is what? Y1, 0.882. As you go upwards, your vapor phase composition increases, hence I am keeping Y1 on top. As it is leaving one plate, it is on the top. From the 2, your vapor which is leaving is 0.76. So that is clear. Now talking about liquid composition. As you go down, composition of A, more volatile component, decreases. Hence, liquid leaving one plate, that is your X1, that is 0.65. And X2 is what? 0.56. It is leaving X2. Okay. So, Y2 and X1 are your operating composition. Okay. So, this is the operating line of your enriching section, right? Yn plus 1 is equal to R upon R plus 1, Xn plus Xd upon R plus 1. Okay. N plus 1 is there, see here. Hence what I am doing, Y2 is equal to X1 into R upon R plus 1 plus Xd upon R plus 1. Is that clear? See, from 2, Y2 is leaving, whereas from 1, X1 is leaving. Okay, substituting the value 0.76 is equal to R upon R plus 1 into 0.65 plus 0.98 upon R plus 1. Solving it, you get your R as 2. So your reflux ratio is what here? 2. So one part is solved. Now, what is reflux ratio? It is L by D. Okay, therefore you get a new relation that your L is equal to 2 times D. Now have a revise over the overall material balance of a condenser in enriching section. See on the top part, vapors are going into the condenser. Okay, that is giving you liquid plus distillate. Hence your overall balance is what? V equal to L plus D. Substituting L equal to 2D, therefore you get your V is equal to 3 times D. Thus, your vapor flow in enriching section is how much? 300 kilomole per hour. Clear? Now, again recall, feed condition is given here. That is saturated liquid. It means Q equal to 1. That means V is equal to V bar. Therefore, vapor flow rate in stripping section would be same as that in enriching section. Hence, your final answer is V bar is equal to 300 kilomole per hour. So, these are some types of questions which can be asked in your exam. That was for today's lecture. Thank you.